In this lab, you will be learning how to use Pivot Interactives, learning how to collect data from it, and learning, getting an introduction to what a position time graph looks like for something that is traveling at a constant speed versus what it would look like if it wasn't. So you're basically going to be given a video and instructions on how to do the analysis of a ping pong gun that launches a ping pong ball at a Coke can. And what you want to do is to track its motion from the time after it leaves the gun to when it hits the can. So what I usually do is I advance it to where I want to start taking data. Maybe right here. And I'm going to turn on the time. And if I click the arrow, then I'll zero it. That will be my first time. So that'll be time 0. And then I'm going to turn on a ruler. And I'm going to put the ruler so that the 0 mark is right on the very edge of the ball. And then I am just going to advance it. And every time it advances, I'm going to, in a graph, I'm going to, a table, I'm going to write down the position in centimeters and the time in seconds. And as I do that, I'm going to end up with a graph that looks something like this. So let me find that for you. So I'll have typed in 0 and 0 for first point, and then when I advance it, I'll say 8 centimeters and 0.00038 seconds, and I'll keep going until right before it hits the can. Now, I'm going to want to make a graph of position versus time, but my position needs to be in meters, but right now it's in centimeters. So I'm going to create a new column beside the position column, and all I do is just click on the 3 dots and say insert column to the right, and then I can name it position and put the units in as M, and then I can just manually enter how many meters there are. So just divide it by 100, move the decimal place 2 places to the left. So 0.08, 0.16, 0.235, etc. I don't want to drop any of the numbers that I have. I don't want to lose any of my precision. And then I'm going to plot position versus time. And to do that, I just, on my graph, I'm just going to, in the X, I am going to choose position in meters, on the Y, and then I'm going to choose time on the X. And then my graph name will be whatever's on the Y-axis, time, versus whatever's on the X-axis, position versus time. Notice that this looks pretty linear, and what I want it to do is I want it to do a curve fit. I want it to draw the best fit line. This looks like a line. So when I click on curve fits, I can choose a variety of different types of functions to fit it to, and I'm going to fit it to a line. If I do that, then I get the generic equation of the line is y equals mx plus b, or in this case, x, which is the position, equals, instead of m, they use a, and x is t for time, and b is the y-intercept. So a is going to be my slope, and it's going to tell me how many meters per second I'm traveling at. And since it's a constant slope, I have a constant speed or velocity. And I started at 0.0235 meters as my initial position. And this RMSE value should be close to 0, and it is. And this R value should be close to 1, and it is. And both of these tell us that the points fit on the curve that we fit. Because I could tell it to fit any curve. And if the RMSE is not close to 0 and R is not close to positive or negative 1, then it's not a good fit. But this is a pretty good fit. So you're going to go through the rest of the lab, learning how to use the parameters for that linear fit to describe the motion of the ball. Remember that if you say the ball is traveling at a constant velocity, you cannot say that it is traveling with a constant acceleration, right? Because a constant acceleration means that it's changing its velocity in some way, either the direction it's traveling or the speed it's traveling at. So you don't want to say that.